All right, 5035 MAA, dynamics and solid mechanics revision. We'll start with revision of dynamics. Faris was very clear that we should revise. So I have a plan. So I'm not taking requests as of this time. Next week, you can ask me anything to solve any question and past papers as well. For this week, we're going to solve question 2 of the revision. Now, all the revision is found on Aula. I found these ones on the 5035 MAA, Journey, Wiki 11, and Dynamics revision. So these are the questions this is the lecture. So these are the questions I'm attempting right now. Just question 2 as instructed by Faris. Question 2 includes vibrations and velocity acceleration diagram. And then for solid mechanics revision, we will do, I think it's this one, yes. We'll do Q1A and Q2A as well. Okay, so let's start with this. So we have a mass spring damper system, mass M, so there is no mass M, stiffness K, damping coefficient C. The mass is constrained to move in a y direction as indicated in the figure. When released from a deflected position, it was observed that successive amplitudes at a certain position were 2 and 1.45 millimeters. The time required to complete one cycle is 0.315 seconds. So let's put these first in numbers. So what we have is that, say, amplitude N was 2 millimeters, and amplitude N plus 1, so the successive amplitude, was 1.45 millimeters. We also know that at the time required to complete one cycle, so the period, that's what it is. Okay, so the time it takes for one cycle to complete is called the period T, capital T, and I forgot what it is. It's 0.315, 0.315 seconds. Okay, now, what do we want to find? We want to find the frequency of free vibration, so the damped natural frequency in hertz and radians per second, the damping factor, the natural frequency of the system, so not the damped natural frequency, the natural frequency, the undamped one, and the mass if we are given the spring stiffness as 8,000 newtons per meter. So let's also say that K is 8,000 newtons per meter. So let's start by part A. So part A asking omega D. What is the damped frequency of this thing? How do we find it? Well, first of all, let's recall what is the solution of a damped system. So for a damped system, harmonic oscillator, the solution x of t, in this case, let's call it y of t because it's in the y-axis, is the amplitude E minus zeta omega n t sine of omega d t plus phi. You agree with me? This is what you should recall from the theory. And so this omega t, this omega d apparently is the frequency of the sine wave. So that means if I look at it like this is the sine wave. Now, all right. And so we have, this is, say, amplitude N. This is amplitude n+1. And one cycle corresponds to, say, this. So this is the period, this is in seconds, and this is the amplitude in millimeters. Agreed? So that also means that this omega d is the inverse of the period. That's the idea. The frequency is the inverse of the period. So we can say very easily that omega d is 1 over t. In this case, is 1 over 0.315. 315, yes, 315. And of course, the period is in seconds. That means that omega d is, this answer will be in radians per second. How much is this? Let me fire up the calculator. Oh, there. What's this calculator? It's huge. And so using calculator is 1 over 0.315, 3.174. 3.174 radians per second, which of course corresponds to how many hertz? How do we find this in hertz? How do you do this in hertz? So remember that omega, we call omega is always 2 pi f, okay, where f is the frequency in hertz. So that means that this corresponds to 2 pi, sorry, this is 2 pi f, fd in this case. And so that means that fd is omega d divided by 2 pi, which is this number divided by 2, divided by 2. No. This number is 3.174 divided by 2 divided by pi. Is there pi anywhere? No, this is scientific. Ah, no, it cleared everything. Ah, Windows. What are you doing to me? 0.315 inverse of this divided by 2 divided by pi. 0.505. Hertz. Easy. Now, let's see what we want, what else we want to find. Here. So this was A. Now let's do B. For B, we are asked to find the damping factor of the system. What is the damping ratio? Damping factor, the damping ratio is the same thing. So let's recall the damping ratio. Damping ratio is C over C critical. Remember, C critical is also 2 omega n m, or the square root of Km. Okay. Is there any other way? Because we don't have mass and we don't have omega n. So this is not very useful. Also, we don't have C. But what we know is that we know an and an plus 1. So we know that this is following a logarithmic decrement. Great. So that's this thing follows the logarithmic decrement. This part here is exactly this. So what we have is that we can estimate this zeta. So estimate zeta. From logarithmic decrement delta. You remember what is delta? So delta is the logarithm of an divided by an plus 1. So in this case, we have the logarithm of AN was 2 and 1.45. So this delta is a calculator. So 2 over 1.45, 1.5 is this, and the logarithm of this. Do we have logarithm here? Function. No. Trigonometry. No. Oh, log, ln. There you go. 0.321. Has this got any units? Logarithmic decrement? No, because it's a ratio of amplitudes. So this is millimeters over millimeters and the log of that. So we have 0.321. And how do we estimate? Well, knowing this, how do we estimate zeta? Well, this is also equal to approximately 2 pi zeta. If zeta is smaller than 0.1. Otherwise, we have to use this. Okay, so this is exactly equal to this, but this is more complicated to use. So let's use 2 pi zeta equals, let's use that, say that zeta is approximately 0.321. Let's say delta divided by 2 pi. So this gives this divided by 2 divided by pi, 0.05. Since it's smaller than 0.1, that's fine. Okay, good. Good. Okay, so we found B. Let's do C. See how easy is this? It's just a matter of using your formula sheet, which I remember, of course, but you have all the formula in front of you anyway. So it's even easier for you. We want to find here the natural frequency in hertz and in radians per second. So the natural frequency, now in this case, we want to find omega n. How much is omega n? Well, omega n, remember, comes from, you know, that omega d is also omega n square root of 1 minus zeta squared. Zeta squared. And so we can just use the inverse formula to say that omega n is omega d divided by square root 1 minus zeta squared. And so this is equal to omega d is, let me find it out here, omega d. Let me also put this. So this is what we found. This is what we found. This is for omega d. For zeta, we found this. So 3.174 divided by the square root of 1 minus zeta squared. So this is zeta. If I square this and I say negative of this, which I can find, so minus 1. So minus 1. And then take the positive of this. And I take the square root of this. Okay, so this is 0.998. It's basically almost 1. Huh? And it makes sense because the damping ratio is very small. So it's very lightly damped. So what we have is omega d was time, this is times, is this the inverse? No. Yeah. So times should be the inverse of this. Okay. So times 3.174 gives me 3.178. Radians per second. So this is greater, omega n is greater than omega d, which is of course the case, always the case, because this number is always smaller than 1. And so for hertz, So this is also equal to, well, of course, it's the same. So it's divided by 2 divided by pi. We got this divided by 2 divided by pi. You get 0.506. There we go. That's omega n. Finally, what do we want to find? What's the last one? The mass, if the spring stiffness is 8 kilonewtons per meter. Well, this is very easy. Remember that the mass, so d omega n square root of k over m. And so omega n we found, so that means that m is omega squares k over omega n squared. So it's just 8,000 divided by omega n squared, which gives, this is omega n. No, it's times 2 times pi. So this is omega n. If I square this, I invert this and times 8,000. This gives 792 kilograms. 0.02. You agree with me? Did I screw up?
I think the answer says 20 kilo.
20 kilograms. Okay, so I did screw up.
I think in your omega d, I think you use FD, not omega d. If you look at
Oh, yeah, I might have. So let me find, let me do this. So it's 3.178, 3.178 squared inverted times 8,000. No, 792.10.
if you calculate omega n, another omega n equals omega d over √1 liter squared.
Yeah, omega
Omega
n is
d.
this 3.178.
I think omega n, the solution says is nearly 20 liter per second. It's 19.97 liter per second.
Let me check the chart. Omega n is square root of 1 minus, no, that's that omega d is, that's omega r. Marius, you're using the resonance frequency, not the damped natural frequency. Okay, so that's a different thing that you use for forced systems. Okay, that was called omega r in the formula sheet, which is very similar, but it's not the same. So guys, help me out. Where did I get it wrong? Is omega n correct?
So omega n is hertz is correct, but its liter per second is not correct.
So this is not.
Yeah, 3.17 is in hertz. It's not in liter per second.
Oh, 3.17 is in hertz.
Yes, 3.18 is in hertz.
No, that's impossible.
Because you put
yes.
FD, the value of FD as omega d.
Yes. Sorry, this is FD. Oh, that's where I got it wrong. Thank you. So this is FD, the inverse of this. So this is in hertz already. Of course, 1/2, which is hertz. So yes, we have done the other way around. So this is FD, this is in hertz. And so that means that omega d is 2 pi FD, which is not this, of course. It's 2 pi, so 2 times pi times 3.174, 9.97 radians per second. Thank you. So this was an oversight of me, and so of course this is also incorrect, because what we have here is the other way around. So omega n is 9.97 times this. So 1 minus 0.5 squared. This under square root is this, the inverse is this, times 9.97. It's in hertz, so 9.98. Sorry, this is in radians per second.
Still different from the solution, another. Omega D is 19.95 liter per second. Omega D. It's 19.95.
Did I screw up this? You say 3?
Yeah, I think omega D is different
Yes,
from
yes. Omega D is 2 pi FD. 2 times pi, 2 times pi times 3.174 is 19.4.
Yeah.
How did I get it wrong?
You forgot 2, I think.
Oh, thank you. Sorry, guys. Just getting a bit. So omega D divided by this. So this is now 1 minus zeta squared is 1 minus 0.05 squared. Is this. The inverse of this is this. And so times 19.94 and 94 equals 19.99 basically radians per second, and divided by 2 divided by pi divided by 2, it's 3.18 hertz. All right, and so here it's just 8,000 divided by 19.99, so 19.99 squared inverted times 8,000, 20 kilograms. There you go. 20.02. Okay. Apologies for these calculations mishap. But I think this should be easy enough. Okay. Can you please explain the 1 over pi bit again? What do you mean the 1 over pi? Which one is 1 over pi? FD. Oh, FD. So time is in seconds. So this period here is in seconds. Okay. So FD in hertz. Yeah. Oh, this is not pi. Yes, this is t. It's 1 over t. So in hertz is 1 over, say, you know that second is, so hertz is 1 over second. So if you invert the period, you get the frequency in hertz, not in radians per second. That was my oversight. Yes. What's the other question? Was there a question here? On here?
I was going to say, could you go back over how you found the damping factor?
Yeah. So the damping factor, I started from the ratio of successive amplitudes.
Well, actually, hold on.
So an divided by an plus 1. So the natural log of this ratio is this number, and this number is the logarithmic decrement, which is equal to this.
Wait, sorry. Do you know before that?
Yeah.
So 1 over the time. That's in hertz.
Yes. No, 1 over the time is in hertz. Yes.
Yeah, and then change it to.
Yeah, exactly. So you just have to use the inverse one. So omega d is 2 pi FD. In this case.
And then you need to times by 2 pi.
Yeah, because
Okay.
1 hertz means 1 cycle per second.
Yeah.
1 radian per second is how many radians there are in a cycle. There are 2 pi radians in a cycle.
Sorry, what were you saying about the damping ratio?
The damping ratio is either this is one way, but in this case we can't use this, so we need to estimate it from the logarithmic decrement. So this delta is the logarithmic decrement. All these equations are in the formula sheet, so you don't need to worry about it. This one in particular is there. Okay.
Where's the formula sheet for 1 over r?
Yeah, 1 over r, because so if you have 1 over r, this here, yeah. If you have 1 over r here, that means that this is n plus r. Okay.
Say that again, sorry.
If you have 1 over r here, it's not successive amplitudes, is r amplitudes after that.
Oh,
Okay, so if you have the first, if you have the first and the fourth amplitude, this is A1, this is A1 plus 3.
Okay.
Okay, so this is 1 over 3. Okay, if it's successive amplitude, of course, R is 1, so this goes away. All right, good. Okay, so let's do this. This is a 4-bar linkage. It's a mechanism, ABCD. There is with one link fixed, and the lengths of the links are given. Let me say this is 50 millimeters. So 50 BD, AB, BC, BD. What? AB is 50. BC is 112. BD, I don't think it's there. Should be AD. No, AD is the longest one. So this is BC. So this is CD. CD. So CD is 75. And this one is 140. The crank AB rotates at constant angular velocity of 50 RPMs clockwise. So we have omega 1. Let's call this link 1, link 2, link 3, and link 4. So omega 1 is 50 RPM. And it's clockwise, exactly as I said. The angles BAD and CDA at this specific time are 45 degrees. So this angle here, let me put this here. This angle is 45 degrees. And this angle is 90 degrees. Okay, no need to write it down. Determine, choose a suitable drawing scale to draw the space diagram for the mechanism shown in figure, which is already here. So what's the space diagram? Draw the velocity diagram. This is the important part. Draw the velocity diagram, including all terminal letters and vector arrows according to the direction of motion, and then find the angular velocity for the link BC and link CD. So we want to find basically VA, VB, VC, VD, and the angular velocity omega 1, omega 2, omega 3, and omega 4. So of course, you know that VA and VD and omega 4 are 0 because that last link is fixed. So we need to find VB, VC, omega 1. Omega 1 is given, so there is no need to find this. We need to find these 4 unknowns. And then we want to do the same for the acceleration. So we want to find the acceleration of A, acceleration of B, acceleration of C, acceleration of D, and omega dot 1, omega dot 2, and omega dot 3. Okay, omega dot 1. How much is omega dot 1? Since we know that omega 1 is constant, omega dot 1 is 0. And we also know that A and D are fixed, so they don't go anywhere. So we need to find 8 unknowns. We have 8 unknowns that we have to find in the end. Okay, so let's start. I have here a very, very small picture of this. So let's start with the velocity diagram. So velocity equations, velocity equation. Remember what is the velocity equation? The velocity of any point. Velocity of any point is the velocity of a reference point plus omega vector, the distance between the 2 points. And this thing is also called VAO. Okay, so this is the velocity of A with respect to O, just the bracket So we can say that the velocity of A with respect to A is VA minus VL. That's what we did in first year. Remember, it's just subtraction of things. Okay, that's all we need for the velocities. For the accelerations, we'll do it later. It's much larger equation, contains more terms, contains 3 terms instead of 2. So let's start. We want to find the velocity of B. Do you agree? So the very first thing, since we know this omega 1, we need to find the velocity of B, which you should agree with me. It's in this direction. It's perpendicular to the link AB. Why? Because if the link is rigid, that means that this cannot become longer or shorter. So that means that B will never move in that direction. And so that means it can only move on the perpendicular direction of dot. We just have to be mindful in which way B is moving. Is it moving up left or down right? Well, of course, following omega 1, it's very easy to see it's moving down right. We can do this very easily using this vector product. But first, let's start by writing the equation. The equation says that velocity of B is the velocity of a reference point, in this case A, plus omega 1 vector R BA. So the velocity of A is 0. So let's start by signing on the point A and point D, because they are the same fixed point, so they have no speed, they have no velocity. This is my origin of the velocity diagram. I'll say that A and D have no speed, so they remain at the origin. Now, VB is a vector that starts from A, so starts from the origin, in this case, and we need to add this other vector here, which is the vector product of these two vectors. Omega 1 is a vector that goes inside the paper. So it doesn't come outside, because that would be for a counterclockwise omega 1. Since it's a clockwise omega 1, the vector goes inside. So a vector that goes inside towards a vector that is RBA. So it's a vector, it's the position vector of B with respect to A. And so that means it's this vector here. This vector here is RBA. So RBA is a vector with a point in B and the tail in A. Agree? Good. So if you put omega 1, which is a vector that goes inside of the paper, over RBA, you end up with a vector that goes down right. Try with your right hand. Put the first vector is inside the paper. It goes towards RBA. You curl your finger towards RBA, and then your thumb points in the other direction. You use your right hand, your left hand. And there you go. You have that is the velocity of B with respect to A. So you get VBA. And of course, since VA is 0, VB is also VBA, and we end up with this vector here. This vector here is exactly what we want. This vector here is VB, which is also equal to VBA. Agreed? And so I can just draw a vector that is how long? Well, first of all, let's draw a vector that is perpendicular. So I'll duplicate this and I'll put it here. And how long? We'll have to check. So we know omega 1. Omega 1 is 50 RPM. So how many radians per second are 50 RPM? 50 RPM is equal to 50 times, so times 2 pi divided by 60. This equals 50 divided by 60 is 5 or 6. So it's 10 over 6 pi, 10 over 6 pi, which is 5 over 3. Which is 5 times pi divided by 3. 5.236. Radians per second. Let me check the chat. Yeah, thank you, thank you, Marius. Okay, so that means that we have this. This is 5.236. RBA is 50 millimeters long. So that this is a vector product. So it's the magnitude of this times the magnitude of this times the sign between these two. Now, since this is perpendicular to the paper and this is in the paper, the sine of the angle is 90 degrees. So theta is 90 degrees. Sine of 90 is 1. Agreed? So VBA has a length of 5.236 times 50, which is equal times 50, 261.8. 8 what? What are the units of this? No, millimeters per second. So this is a velocity, a linear velocity. And so let's say that you have chosen that 1 centimeter is 100 millimeters per second. So use a scale factor, Let's say that 100 millimeters per second is 1 centimeter on paper. So that means you have to draw a vector that is 2.6 centimeters. And let's say this is 2.6 centimeters. So this is VBA, which is equal to VB. So this is point B. And this is 261.8. Let me do it here, 261.8 millimeters per second. Okay, how do we find C, the velocity of C? Well, the velocity of C is the velocity of a reference point. Now, which reference point do we use for C? We can use B or you can use D. So let's start with B because B is what we found already. Okay. B is now completely given. It's a point that we found. Velocity of C is the velocity of B plus omega, which omega? Vector R BC, sorry, CB. Which omega is this? Omega 2, because we said this is 2. Because looking at the reference point B, they are on link 2, both of them. So we have an issue here. We have VB, but we have no idea how much is omega 2. Agreed? We don't know. But we do know that this thing, which is, remember, this is always VC with respect to B. This VCB, we can find the direction. Because we know this is a vector product. So this is a vector that goes either outside or inside the plane, omega 2. And this is RCB, which is this vector here. So it must be perpendicular to both. And that means it is perpendicular to RCB. So it's this direction. Agreed? Okay. So this direction, let me see if this is perpendicular, not quite. Yeah, select that. This direction here is the direction of VCB. And that's it. We don't know anything else. So we must stop here, but we can draw a line. We can draw exactly this line. And this line will tell me this is the B line, sorry, C line with respect to B. Agreed? So this is the line that C, velocity of C is VB, this vector here, plus another vector that must be in this direction. I don't know where it stops. I don't know if it's in this direction or in this, and I don't know how long it is. So let's say this is the line I'm looking for. And also do this. So this is the line I am looking for. It's infinitely long and I have no idea where it stops. So let's find out what is the C line with respect to D, because now we can do the same thing using a different reference point. So we say that VC is also equal to, by just changing reference point, VD plus omega 3 vector R CD. Agreed? And now this is 0. So that means we can start from here. And this vector here is, which direction is this vector? Well, it's perpendicular to omega 3, of which we don't know anything about, but we know that this is VCD, velocity of C with respect to D. And so RCD is this vector here, RCD is this vector. With the point in C and the tail in D. And so that this one, this VCD is perpendicular to omega 3, that means it's in plane, and it's perpendicular to RCD, it means it's horizontal. Agreed? And so that means that it is an horizontal line that passes through AD, passes through this point. And of course, I've chosen very, very wrong everything else. If I can make this better. There we go. And so this is the C line. With respect to D. And we know that C must lie on this line and on this line at the same time. So where is C? Where is C? It must be here. And so what is VC? Well, if this is, now looking at this equation, this is VC is VB plus VCB. VC is VB plus VCB. This vector here is VCB. And from this one, we say that this is VC is just VCD. So this is also VC. This is VC. Come on. No. There we go. This is VC, which is also VCD. How do we do this? Well, how can we find out how much is this? Well, you need to actually measure it, because you know that this is 2.61 centimeters, and it corresponds to 261.8 millimeters per second. So now you can find how much is VCB and how much is VC. Okay, so these ones will be, and we got numbers for these, Lynn?
Sorry, there's no
Mario says,
solution.
okay. Yes, please. And Mario says, ask, can you please explain again why it is horizontal? Well, it is horizontal because look, this VCD, so this VC is also VCD, is also equal to VCD. this is a vector. This is a vector product. This VCD is a vector product. And it's a vector product of omega-3, which is either outside or inside, we don't know. It's outside or inside the paper. And RCD. RCD is vertical. So vector product means it must be perpendicular to both. And that means perpendicular to omega-3 means it's in the plane. And perpendicular to RCD means it's horizontal. How are we supposed to do this online in the exam? Well, you just do it on paper. I mean, I can't, I find myself in a position for which my my iPad, or at least the note-taking application I'm using, it doesn't let me understand how long is this vector, but you can measure it. I mean, if I had, even if I had my ruler, a ruler with me, I could measure it. As long as you have a ruler, that's fine. And if you're asking how you do this, how do you put this on the actual submission point, you can just take a picture. So as long as you take a picture, put it in a Word document and produce a PDF in the end, that's fine. Okay. Yes. What's the question?
Yeah. So you know when it comes to the forming the shape, vector shape, vector.
Yeah.
How do you determine like the angles in between like each vector?
I don't determine the angles. I just draw whatever is. So I say perpendicular to this. Now we know that this is 45 degrees. So I also know that this is 45 degrees if you want. Okay. Okay. I mean, you don't need, as I mean, like your lines perpendicular to space diagram. Yeah, exactly as I'm doing it. You can do it on paper. It's very easy. You just draw a line that is perpendicular to this, because in the paper you will be given the figure and the blank space to produce the velocity diagram, say. So you can definitely find the perpendicular one. Okay. Yes. Cheers. Yes.
Can you use CATIA to solve these kind of questions?
You can use CATIA to solve these kind of questions. It's very easy. Also, you just have, if you know the angles, yes, of course. Now this one, you might not know the angle, but you can calculate the angle. Okay? The angle of this. But again, it's you can use whatever you want, as long as the final result looks like this and has all the appropriate labels. That's fine. So what we are interested in is the values of all these vectors, the arrows, the points, so A, B, C, D, and we need, no, that's it. And all these labels here. Okay, so as long as you label it exactly as I did, it's fine. So if it looks like this, it's correct. Even if it's a bit out of scale or a bit, it's fine. Okay, it doesn't matter because it's a graphical method. We don't expect you to be 100% accurate. All right? Yes, what's the matter?
So for the exam, would you accept us using CATIA?
Again?
For the exam, would you accept us using CATIA for this?
Yes, I would. Okay, I would. And I'm sure that Faris does as well. I mean, you should ask Faris, but I'm sure he's okay with it. So as long as you know what you're doing. I mean, I think it takes more time with CATIA than by hand, because or at least you start doing it by hand and then you do it properly on CATIA. That might work. But again, you're doing it online, so use whatever tool you feel is the best for you. Whatever works for you, just use that. As long as you can put it on a Word document and produce a PDF in the end, that's fine. Okay, don't submit your CATIA files because we don't know what to do with them. All right. All right. That's it. We found VA, VD, they are both 0. We found VB, this length here. We found VC, which is this length here. We need to find omega-2 and omega-3. Omega-1 is 50 RPM. Omega-4, sorry, Omega 1, 2, 3. Omega 4 is 0. So we need to find what is omega 2 and omega 3. How do we find omega 2 and omega 3? Well, it's easy. It's here. See, it's inside here. Everything is inside the equation. VCB, which is this length, this vector of this length, is this beast. So I can say that omega 2 is, so the magnitude of omega 2 is the magnitude of VCB divided by the magnitude of RCB. And I can say that the magnitude of omega 3 is equal to the magnitude of VCD divided by the magnitude of RCD. Very easy. Now, since you know these, the only thing that's left is the orientation of omega 2 and omega 3. Do we know it's clockwise or counterclockwise? Well, that's also easy. And it's also in this equation. So VCD, it's this vector here. Okay, so this VCD is this. So VC, the velocity of C with respect to D, so as if D was fixed, which is fixed, that's why they are exactly the same, is this. So that means that VC is this. This is VCD. Now, if this is VCD, which direction is omega 3? Clockwise or counterclockwise? What do you think? It must be clockwise. Okay, it must be. Because otherwise VCD doesn't go in that direction. Let's, so omega 3 is clockwise. And what about omega 2? Well, VCB is this. So VC with respect of B. So if B was fixed, VC would be going in this direction. So which direction is omega 2? Say again? Counterclockwise. Okay, you agree? It must be going in this direction. So this is counterclockwise. And so we have complete information now. We need, though, we need the velocity acceleration diagram. I'm going to do it here. Let me add the page. For the acceleration diagram, the acceleration equation is the acceleration of any point is equal to the acceleration of a reference point plus the omega vector RAO. Remember, this is the centripetal acceleration plus the tangential acceleration. This one is what we call AN AO, and this is what we call AT AO. Agreed? Yeah.
You know, you said it was going counterclockwise and clockwise. Could you go back to that?
Yes.
For the diagram,
Yeah.
from B to D,
Yeah.
it goes upward. It goes. Yeah, so that's counterclockwise. Like this. That's what was it? BC. Like that.
Yeah.
It's going like that.
Yeah.
Oh, how come you drew it?
I mean, that's C with respect to B, as if B was fixed. Now, B is not fixed. So the absolute velocity of C is right. The absolute velocity of C is this. It's to the right. So on a fixed observer, C is going to the right. But if you were sitting on B, you would see C moving top left. Okay, that's the idea.
For
CD,
Yeah,
how is it, which direction is it?
what do you mean for?
For CD, it rotates in the clockwise direction?
Yes, because the velocity of c with respect to d is equal to the absolute velocity of c, which is right. And so c is going right. And so that means if d is fixed and c is going right, this is going clockwise.
Oh.
Okay.
Omega 2 is confusing with that.
So what's confusing?
See, omega 2.
Yeah.
What do you mean by that?
So if b is fixed, v of c with respect to b is this.
Yeah.
Okay.
Get that,
And
yeah.
so if b is fixed, the only way for c to move in this direction would be if omega 2 is counterclockwise. Agreed? So try to put b like this. So this is b is fixed. C is going in this direction. See.
Yeah.
So omega 2 is counterclockwise. Must be. Okay. All good?
Yeah.
Good. So this is for accelerations. And so we just have 3 terms instead of 2. It's just a bit more complicated, but not too much, because this one, this is also called acceleration. Let's call it centripetal acceleration, AC, rather than normal acceleration. It doesn't matter, it's the same. This one is parallel to AO, but with the point in O instead of the point in A. And this one is perpendicular to AO. Okay, so this is parallel, and this is perpendicular. So let's start again. We have that A and D are also fixed points because their acceleration is 0. And we can now find these ones are all given because all the omegas we found earlier. So this one is always known. What is unknown is this one. So let's start with B. Yeah, so the acceleration of B is the acceleration of A plus omega 1 vector omega 1 vector R BA plus omega dot 1 vector RBA. Of course, omega dot 1 is 0 because omega 1 is constant. We can go here and say, don't need this, and you can calculate this. How much is this? This is omega 1 squared RBA, which is equal to 5.236 squared omega 1, 5.236 times 5.236 times 50 millimeters. So this is 1,370 millimeters per second squared. So let's say 1.3 meters per second squared. Okay, and 1.37. And so we know that AB is a vector that starts from A, so starts from here. We add a vector BA, so BA is a vector, RBA is this, but we want a vector that is parallel to RBA, but in the opposite direction. So it's a vector that points in this direction towards A. So I can take this. Place it here and say that I want a vector that is pointing in the opposite direction. Okay. So this is AC. Remember, this is also AC BA. This one is AC BA, which is also equal to the acceleration of B. How do I know it is equal to the acceleration of B? Well, this is 0. AB is 0 plus this plus 0. So ABA centripetal is also AB. And so this is point B. Easy. And that's equal to 1.37 meters per second squared. Now we find the acceleration of C. The acceleration of C is the acceleration of B plus omega 2 vector omega 2 vector RCB plus omega 2 dot vector RCB. This one is given, we just found, it's this. This one we can find, we can calculate very easily. This one is the acceleration C, this centripetal acceleration of C with respect to B, which is equal to omega 2 squared times RCB, which is a number because RCB is given, omega squared we found earlier. And this one is unknown. This one is unknown, but we know that AT CB is perpendicular to RCB. That's the idea. So let's draw this one. This one is, let me draw this in orange. So this is RCB, but with a point in B instead of C. So it's in this direction. So it's this vector here. And starts from this point. So it must pass through this point here. And let's say this one, no, so let me, so this is here. Yeah. So this thing, say, goes here. So this is ACCB. And we also know it has a certain number of meters per second squared, which I'm saying is this long, but I'm not sure. Okay. We also know that ATCB is perpendicular to RCB. That means it's also perpendicular to this, because this is parallel to RCB. This is perpendicular. So finally, whatever vector I have is this, that is perpendicular . This one is ATCB, whatever this vector is. And this is the C line. Well, let's call this the C line with respect to B. And now we do the same for with respect to D. So first we find the acceleration of C equals the acceleration of D plus omega 3 vector RCD plus omega 3 dot vector RCD. And again, this is 0. So this is 0. This is the acceleration centripetal CD. This is the acceleration tangential CD.
I don't know why you said there was no tangent acceleration, but the first one.
Yeah.
Why did you say there was none in the first one?
Well, because the tangent acceleration is the vector. There is no vector on this line yet.
No, not that one. From
This
the very first A to B.
A to B.
It's the very
Yes.
very first one.
It's a centripetal acceleration
Why not tangent?
because it's 0. Because omega dot 1 is 0. So we only have centripetal acceleration for our first link because omega 1 is constant. Okay, good. So we have everyone every acceleration has 3 components, but some of them sometimes are 0. In this case, 2 components are 0, so the acceleration of B is only this. So it's only one part. The acceleration of C is this plus whatever is this. This plus whatever is this, which I don't know. But I know it's in this direction. It can be up or down. I don't know. I have no idea. Now the acceleration of C is also starting from D, this, plus this, which is RCD. It's a vector, it's a vertical vector pointing at D. And of course, this means that I screwed up the placement of these. So this is RCD. This vector here is ACCD, which is a certain number of meters per second squared. And finally, this must be, this one is perpendicular, so perpendicular to this. This one is the C line with respect to D. And so D must lie on this line, so C must lie on this line and on this line at the same time. So that means this point is point C. And so we can now say that this vector, well, this is the C line here, and I can say that this vector here is the acceleration tangential CB, and this vector here is the acceleration tangential CD. Agreed? But what is AC? Well, AC is the sum of 0 plus this plus this. So is the hypotenuse of this triangle, AC, this plus this in a vector way, this plus this, or it is AB plus ACCB plus ATCB. So finally, I can say that AC is this vector. This vector is the acceleration of C. Agreed? We can go there in 2 ways. AC is this, so 1, 2, 3, 1, 2, 3, or AC is this, 1, 2, 0, 1, 2. Agreed? We can get there in 2 different directions. Any questions? Now, the only thing that is left is to find omega 3 dot and omega 2 dot. Omega 2 dot is this. Okay, so it's ATCB, the magnitude ATCB divided by RCB. And omega 3 dot is the magnitude of ATCB divided by RCB. Directions, it's exactly the same way. So look at ATCB. ATCB is going like that. So ATCB, let me copy this and paste it here. So ATCB, that means the acceleration, the tangential acceleration of C with respect to B, as if B was fixed, it's in this direction. So that means that omega 2 dot is clockwise or counterclockwise. Come on. B is fixed. The acceleration of T is going in that direction. So that means that omega 2 is clockwise. Okay, it must be. And omega 3 dot, well, ATCD. So C with respect to D is going in this direction. With D fixed. So that means that omega 3 dot is counterclockwise. And so that means that see omega 2 is counterclockwise and omega 2 dot is clockwise. So omega 2 is decreasing in time. And omega 3, which is clockwise and has an acceleration that's counterclockwise, it's also decreasing in time. Okay, so during this movement, the omega 2 and omega 3 are decreasing in time. So they are decelerating, they are slowing down. Okay, any questions? I think it took us a long time to do this, but it's fine. So I'll give you a short break, 5 minutes. Yes, 5 minutes only, because we have some other things that we have to tackle here for statics. Yeah. Questions, and I'll check the chat. No questions in the chat. Very good. How did we find the direction of vector? Which vector? Omega 2 dot, omega 3 dot? Saim, which vector are you talking about?
I can tell. I can fucking tell.
Omega 2 and 3. The dots or non-dots? The angular velocities or angular accelerations? Non-dots, so these ones. So the angular velocities here. It is exactly in the same way. So you have to look at the part of the equation that contains omega 2. So in this case, VCB is the vector you have to look at. So VCB is this vector here. And so VCB is the velocity of C with respect to B. That means the velocity of C as if B was fixed. So the velocity of C as if B was fixed is in this direction. And so omega 2 is counterclockwise, because if I fix this and VC is going in this direction, that means that omega 2 is clockwise, counterclockwise. In the same way, you look at VCD, which is this vector here. So this is the velocity of C as if D was fixed, which is exactly the case. That's why it's also VC absolute. So this is going right. This D is fixed. And so the only way this can work is if omega 3 is clockwise. Omega 3 is clockwise. Okay. Cheers. Yes.
What happens to AB acceleration? Like if you look here,
What happens to the acceleration?
this one, this one's going to be like rotating backwards this way and rotating up.
No, it's
Rotates downwards.
it's not. You're confusing. Acceleration changes the velocity.
Yeah.
So you can't move. So it moves in the direction of the velocity.
So don't think about it in terms of that, right?
So if you want to look at the movement, you look at the velocity diagram. So okay, because the velocity changes the position.
I'm doing it like this.
The acceleration changes the velocity.
Yeah, I've got this and then I'm like, what we say, 1,370,
Yeah.
and then I'll say that's say 1.37.
Yeah.
So I'll just go like that. Scale up. Down,
Yeah.
basically.
Yeah, that's fine.
That'll work. This will be alright. Down a bit there.
When's your fee session?
Today, 3 to 5. But
Next week.
yeah, yeah. If you send me an email anyway, if I'm free, I'll just meet you. So don't worry. Just send me an email always, because otherwise I will not come down.
Also, I know that you have to like think about it logically in terms of what direction it will go, or can you just extend the line far and think about it as in where's it going to intersect? Does that make sense?
Yes, but you need to find at least 2 lines, because otherwise how do you make
For
them
example,
intersect?
CD, you know CD is going to go centrically towards where it's rotating.
Yeah,
So then you can just draw a line going downwards. That's
well, you don't know if centripetally is gonna go towards this, because it goes towards the only if it's rotating at constant speed.
So like, say you're like, that's nice. Wait, one second.
Yeah.
Say say you know it's from 0,
Mhm.
you just draw a long vertical line.
Yeah.
And then you say, okay, cool, so it has to go to this point. We know that.
No, we don't know that.
We don't know that.
How do you know that?
Well, you know this goes that way,
Yeah,
and you know this line, you don't know the direction of that line.
yeah.
So you have
yeah,
this line.
but you don't know if this is going down or up.
So technically, could there be another answer?
Yeah.
Which is one which is up this way,
Yeah.
one up that way, and then
Yeah.
going across that way.
Exactly, but that happens if you are rotating in the opposite direction. In fact, if this is rotating, if omega 1 is clockwise, you get this. If omega 1 is counterclockwise, you go the opposite one.
So we're constrained to saying that's clockwise, or we all know. Or would that one to be right as well? No.
Because in this particular thing, you're doing omega 1 clockwise. And at this instant of time, this is the acceleration value. Yeah, on a different instant of time, this is a different one.
Oh.
So this is for this instant of time.
When that's going clockwise.
Yeah, when this is going clockwise.
I thought the acceleration is 0, tangentially. Do you know what I'm saying?
Yeah.
I think I get it anyway.
Yeah, but the fact that this is going clockwise, it means that this has a certain omega and there's a certain omega dot that's based on this omega. So
Yeah.
see, the fact that you have omegas here means that it depends on the velocity diagram. And
Yeah.
the velocity diagram depends on the fact that omega 1 was constant and omega 1 was clockwise.
Okay.
Okay,
Cool.
so everything is interconnected.
Yeah. And 1 second. For the omega 2,
Mhm.
you know from here, for example, the velocity
Mhm.
to c is this one, which I measured to be that.
Yeah.
To put that in there here, you know that V3 is this long one here.
Yeah, but you can't do this because these are all vectors. And you can't sum numbers. These are the magnitudes of these vectors,
Oh,
and it doesn't work like this.
so
So this is a vector sum.
So I
It's
have-
not a sum.
so would I have to work out the angle and then get the components?
Yes.
I have to do it.
If you want to do it like, if you want to do it in the analytical way, everything is a vector. So you split in the X direction and Y direction. And then you
So if I wanted to work out, say I have this and I want to work out omega 2, how would you do it? What's the quickest way?
VC is completely along X. VB is as an X component and the Y component, of which you know the angle. So you can find the
So the quickest way basically is just literally take that apart. That's going to be completely X.
Yeah.
That's going to be that and that.
Yeah.
So that and that
Yeah.
component.
and then you can find the components of the resultant,
So you have
which you know.
I and J component, if you want to do that way.
Yeah.
Add, so minus that minus that one.
Yeah.
Divide them by that one. Then you get omega in terms of a vector.
No, you get the magnitude because this is a vector itself. All of this is a vector. Once you find the components of this vector, Then you can find the magnitude of that vector, and then you can do this division. Magnitude of that divided by RCB.
Wait, so if you get VC minus VB, which is going to be still a vector,
Yeah, it's a vector.
and then you divide that vector,
VC minus VB, you find the vector. You
Yeah.
find the magnitude of that vector first,
okay,
and then you divide by RCB.
okay, okay.
That works.
Okay, I got you. I got that. Okay, cool. I got you. Thanks.
Cheers. All right, guys, let's resume very briefly because the statics part, I believe it's a bit easier than the dynamics. Do you agree with me? You should probably agree with me that the statics is a bit easier. It's always the case because dynamics is just statics with other things. Okay, basically. I mean, even the equations of motion, statics, dynamics. Second. The last question is, I think, is week 3. Is it week 3? If I go here and I check the weeks, week 3 is where we have no vibrations. Week 2, or probably week 4 then. No, week 5. Yes, week 5. So this question here was from week 5, and vibrations were from week 3. Now this one is very long. So for the steel beam with these boundary conditions, we are doing part A only. State whether the beam, show the free body diagram, write the equilibrium equations, and state whether the beam is statically determinate or indeterminate and why. Now this is first year stuff. Okay, so this should be quite easy. So how many reaction forces we have here? What kind of support we have in A? Pin. That means we have 2 forces here. And we have a roller in B, as you said, this is B1. Okay. So you have 3 reaction forces. How many equilibrium equations we have? 3. 3 reaction forces. Does it mean is it determinate or indeterminate? Determinate. Oh, that's good. So this is a determinate beam. Three equations, 3 unknowns. And so let's write the equations. Should agree with me that there are no horizontal actions, so AX is 0. That's my first very simple equation. Easy. In Y, so this is in X, in Y, and in Z around a certain point. Which point do we want to calculate the moments about? Let's say A. In Y, we have AY minus 8 plus BY minus, how do I treat this?
As a point load.
Yes. How much is the equivalent force?
45.
So it's 15 times 3. You agree with me? Good. Problem, 2 unknowns in one equation. So we can't solve this as yet. We have to wait for the other equations. So let's write the other equation. And the other equation is, let me get this larger as well. So the other equation is a moment equation, and the moment around A, that means AX is not, doesn't give any moment. This doesn't give any moment. So we have a moment, which is a clockwise moment, so minus 20. This is clockwise as well, so minus 8 times perpendicular distance, 3 meters, plus by counterclockwise plus 5 by. And this is applied here. This is the equivalent force, which we said is 15 times 3. And it's applied in the middle. And that means it's at 5 plus 1.5. So it's 6.5. And this is also negative. So minus 15 times 3 times 6.5. This one is an equation with a single unknown. We can find by and ay quite easily. Yes.
need to,
because the moment is already in kilonewton meters. This is kilonewton times meters. This is kilonewton times meters. This is kilonewton meters times meters gives F equivalent times meters again gives kilonewton meters. This is already kilonewton meters. A moment is a moment. That's it. And since it's 20 kilonewton, since it's clockwise, it's negative 20. Okay. Yeah, it's applied here. It's applied here, but it doesn't matter. It's already kilonewton meters. That's it. It creates a global rotation of the entire beam. All right. So help me out. How much is By? So By is, you see, ASIA says 67.3 kilonewtons. Kilonewtons, you should write it the other way around. It's kilonewtons, like this. So 67.3. Kilonewtons. And how much is AY, conversely? So AY is just 15 times 3 plus 8 minus By. Minus 14.3 kilonewtons. Thank you. So that means that AY goes in the opposite direction, as I said. It must be because that moment is trying to topple the beam. See, all these forces are trying to topple the beam around B, so A is keeping it fixed down. Okay, that's part A. This is done. Write down a generic description for the bending moment that covers the entire length of the beam using Macaulay's method. Now, we need to use Macaulay's method to find M of X. Do you remember Macaulay's method? So we start AX minus AY X minus 0 to the power of 1. Of course, this one will not give any moment starting at here. Do you agree? Never gives any moment because X minus 0. No, this gives moment. The forces here never give moment. So let's start with M of X. So this is kilonewton meters, is AY times X minus 0 to the power of 1. How do I know? Because this must be kilonewton meters. Agreed? Kilonewton meters. Plus, sorry. Yeah, plus M0, which is 20, X minus 1 to the power of 0. Why to the power of 0? Because it's already kilonewton meters, so this one must be nothing. Why is it positive? Because it says so in the, if you go in the Macaulay's method tables, let me do that. Sorry, I think I screwed up. This one, yep. So if you go in Macaulay's method, Macaulay's method was week 9. Yes. Macaulay's method table. There you go. It's counterclockwise is negative. So since our is clockwise, it's positive. Okay, just refer to the table always. Nope. x minus, sorry, this is not -1, but -2. Because this is applied at 2 meters away from the start of the beam. Then we have negative 8 kilonewtons times x minus 3 to the power of 1 plus by x minus 5 to the power of 1. And then we have minus, so plus minus 15 divided by 2 x minus 5 again to the power of 2. See, this is kilonewtons per meter times meter squared gives kilonewton meters. Everything checks out. Just have to remember this. This is found in the tables, W0 divided by 2. And since this load goes until the end of the beam, there is no need. There is no need for the fake load, remember? Yes.
Should not be -8 times x minus 4.
X minus 3. 2, 1. It's 3. 3 meters away from the start.
Oh, sorry.
Yeah, okay. All right. So that's it. Write down the generic expression. Done. Also identify and write down the equations that are representing the boundary conditions. This we missed this. So the boundary conditions also called compatibility equations are that V of A is 0 and V of B is 0. V of A and so that means that V of A is 0, V of 0 is 0, and that means that C2 is 0. And V of 5 is also 0. And that means that we can find C1 to be something, something. It creates the same kind of moment as 20, but they are the different sign. Does the sign being negative only apply to moments? Yes. Yes.
Are the boundary conditions always located where the reaction force is?
Yes.
Okay. And then-
So boundary conditions are always where the reaction forces are. If you have a reaction force, it's displacement. So V of 0, V of 5. If it's a reaction moment, it's phi of 0. Phi, okay, it's the deflection. Sorry, it's the slope that is involved. Okay. If you have this fixed support, the fixed support has a moment and a force. So in this case, you have phi of 0 equals 0 and V of 0 equals 0. This one is for the moment and this one is for the force. Okay. So in this case, we have two forces only. So we have AY and BY. We have AY and BY. So we have AY means VA is 0 and BY means VB is 0. Okay, let's go on. Here says use all the equations to find all the unknowns. Well, I'm not be going through that because it's very complicated. Well, it's just long. It's not very complicated because using the Euler-Bernoulli bending theory, we know that the second derivative of the deflection is the bending moment diagram over EI. Okay, so we can just integrate this twice. We can integrate this expression over EI twice to find V of X. Okay, so phi of X is the integral of minus M of X over EI dx between 0 and L, and V of X is the integral between 0 and L of phi of X in dx. That's the idea. So that the first derivative is the slope and the second derivative is the bending moment. So that means that the first integral is the slope and the second integration over that is the deflection. All right, this is the state, the things we've done. And here you'll find C1. And here we'll find C1 and C2. Okay, find both of them. Write down ready-to-use equations for which the deflection and slope can be calculated, and this is what we've done. Find the deflection at the free end of the beam. So in this case, we have to do V of what? V of the deflection of the end of the beam here is V of 5 and 3/8. It's V of 8. So once you find an expression for V of X, you just put 8 in it and find V of 8. The height of the beam is 100 millimeters based on bending moment only. Find the minimum required yield strength for the beam material. Okay, so basically it says once you have the bending moment, what is the stress caused by this? Let me add the page. So a stress caused by this is M over I times Y. We know the cross section shape. We know the sign will change when we are going to derive the M of X. Yes. So sigma is M over I. M is M of X, of course. I is always the same. Y is always the same. So sigma also changes with X. So you can find what is the maximum stress in the beam. Okay. Y is 50 because it's 100 divided by 2. It's the section is 100 millimeters tall. And so, and then it says if a beam with the same cross section was used as a column with both ends built in and subjected to an axial compressive force only, determine the critical length of the column above which this is just buckling. Okay, so the buckling says that this is the beam. And you have to find PE, which is N squared by EA over L. So we have all the information you need. And you need to find L. What is N in this case? Sorry, this is N, not N squared. N is 4, thank you. For fix. Again, go back to the original lecture slides and you'll find all the formula sheet in it. In this case, you have to find what is the length that causes this critical load. Okay, looking at this instead, apologies, I'm going a bit fast because we only have 10 minutes left, really. We need to do free body diagram, equilibrium equations, reaction forces and moments at the support, identify internal forces and moment at the section shown. We basically want to find this. We want to see what's happening here. Remember what we did. You can use the sum of moments equals. Let's call this one F1, this one F2, this one F3, and this one F4. So we can say that this vector from this section, this is R1, this is R2, and this is R3. And so you can say that this is R1 cross product F1 plus R2 cross product F2 plus R2 again cross product F3, because F2 and F3 are applied at the same point, plus again R3 vector product F4. Okay. And then you just have to find an expression for R1. The vector expression for R1 is, this is the y-axis, this is the x-axis, and this is the z-axis. So R1 is completely along y, so it's 200j. Okay. R2 is 500j. R3 is, I believe this is exactly in the xy plane, so that there is no z, and it's 500j and 300i. So R3 is 300i plus 500j. And we need to find the forces as well. So F1 is 12 minus k, so minus 12k in kilonewtons. F2 is this one, which is plus 8i. F3, it's this one, which is minus 10j. And F4 is minus 15k. Okay, now we have these. You can just remember that I, j, k. Remember this, and then you can do this. So this is 200j times minus 12k plus 300, sorry, no, this is R2F2, so 500j times 8i plus R2F3, 500j times F3 is minus 10j plus R3 is 300i plus this, so this one is plus 300i plus 500j times minus 15k. Okay, so using those things, we have this is minus 12. So j times k, so j times minus k, so j times k, j times k and change sign. So j times k is I, change sign is minus I. So minus 12 times 200, it's minus 2400. So this one is minus 2400 I. This is this. This is 4000. J times I. J times I is minus k. I times j is k. J times I is minus k. This is minus. Plus jj. What does it mean, jj? Zero. Zero. Because they are parallel, so they don't have anything. And this one is two components. I times k. I times k is minus j, but this is minus k, so it's plus j. So plus 300 times 15 4,500. I times k is minus j, but this is negative k, so it's j. And this is 500 times 15, and it's 7,500. It's j times k, and it's I, but it's negative, so it's minus I. Minus 7,500 I. So using these, it's minus 9,900 I plus 4,500 J minus 4,000 K. And this is the sum of moments about the section of interest. Okay. Now this one is mx, m around the x-axis. This one is my, m around the y-axis, and this one is mz, m around the z-axis. And we just have to find out which one is torsion, which one is so let me do that as my last step. We have fx, fy, fz, mx, my, mz. Some of them are torsion. So this is the section we are interested in. And so the y-axis is normal. So Fy is the normal force. And that means My is the twisting load. And that means that everything else is a shear force, Vx, Vz. And we have Mx and Mz as bending moments. Okay, so these two are bending moments. These two are shear forces. Now we have normal force and twisting load. So you can find here the stresses. So V of x gives tau yx. This gives sigma y. This gives tau yz. Mx gives sigma y. Mz gives sigma y. And t, this one gives tau y, who knows? Who knows, because it depends on which point you're looking at that particular thing. In this case, if the twisting torque is my is positive. See, my is positive. That means that my is positive, means like this, t. And so that means that at A we have t, y, z positive. So this is tau y, z. And at B, you have this one, which is tau yx, also positive. Okay? So depending on which point you're looking at, you have a different tau. Since you have to find it for both points, you have to do this twice, one for point A and one for point B. Okay? And these ones, very easy, you just find them from the formula. Sigma y is n divided by A. Sigma y here is mx. So this sigma y, as an example, this sigma y is mx over ix times z. And this sigma y is mz divided by iz times x. How do I know this is z and this is x? Because this is what's missing. Y, x, z, y, z, x. We must have all three coordinates involved. This one is very easy. And this one is also quite easy, VQ divided by IT. And this one is T over J times R. Okay. That's it. I think I'm done. Have you got any questions? No questions? Yes. What week is this? This week, I think it's week 7, 9. So week 8 should be special stress state. No, this is week 7 then. Combined loadings, yes. Second?
Just scroll up to the values you got.
Yes. Yes.
What's that? Where did I find those slides for the tutorials?
On Aula.
I've tried looking for them. I couldn't find them.
Are you on 206 or 5035?
53.
So can you see this page?
Yeah, I see this page.
So what is that you don't see?
No, the notes you do on the slide shows.
My notes.
Yeah, the notes.
They are in the tutorial. Scroll all the way down, you find the tutorial recordings. This is my tutorial. Okay. That's my audible voice, and this is tutorial 7 PDF. Is all that we did. Okay. And it's in every week. So scroll tutorial, session 3 tutorial all the way at the bottom. Okay. Thank you very much, guys. If you have any questions online as well, let me stop recording.